All right, I'm back. Yeah. So, where were we? You know what? Here we go. Let's do this one here. Yeah. Okay. Good. So we talk about these proteins on the membrane, and we talk about that this protein can provide the channel or carrier for facilitated diffusion. They can also provide the active transport to move things from low concentration to high concentration. An example is the sodium potassium ATPase. And there are two other mechanisms that they can move things across the cell membrane. One is called endocytosis, and basically that engulf a substance and eaten it into the cell or release it. So when they eaten it, it will form these vesicles. This endocytosis has two ways. One is called phagocytosis. One is called the phagocytosis. And this one is shown here. This one only can only be done by, sorry about that, can only be done by a selective type of cells. Not all cells can do phagocytosis. The other one is called pinocytosis. That's right here, pinocytosis. Pinocytosis are very common in all cells. So cells can form these vesicles, import. The difference between these two is that phagocytosis can eat a large stuff. Pinocytosis is for the small molecule. And all these have this receptor-mediated endocytosis, means that they don't eat anything. They eat what they can recognize. So when this particle move, diffuse around and attach to the receptor, here cell would have a receptor right here. Cell would have a receptor. So only when the receptor can recognize this particle, then they will engulf it, or they will conduct this endocytosis. So this is receptor-mediated endocytosis and pinocytosis. That here we have this receptor, binds it, engulf it, form the vesicles. You can see that they basically is a pinch off from the cell membrane. So here is a cell membrane. This blue is cell membrane. So they basically form a little like a pit, and then pit pinch off. Then here is vesicles containing these particles inside of these vesicles. They can be in endocytosis. Another example is here that substance can move from one side into, this is blood vessel, from blood vessel intracellular into the interstitial fluid. So these are the receptor-mediated endocytosis. And one thing you need to know that these vesicles, so this vesicle is also a membrane-bounded organelle. This is an organelle, and this organelle basically have the same membrane as the cell membrane, as the plasma membrane. in addition to the protein and in the cell membrane, we also has the carbohydrates in the membrane. So they are the decoration. We have three types of decoration in the cell membrane. They are the proteoglycans. Proteoglycan is large, like structure outside of the cell. So here is the cell and outside of this proteoglycan. Okay. And another is smaller one, glycoprotein. So this one is that, let me use this one here. So here we have the cell. And here we have the receptor, we have the protein. Okay. And these glycoproteins are the proteins, are the glucose attached to the protein. So can I change color? Can I change color? How can I change the color? Not seeing anything like that. Okay. All right. So here, if we have the carbohydrates will bind to it. Binds to it. Yeah. So that will be the yeah, very annoying. Nothing is perfect. Binds to that protein. Say this is say this is the so this is a protein, then it will bind to it. I don't want to identify. Okay, so binds to it. And this, if it binds to protein, it's called the glycoprotein. If it's bind to the lipid, this one is lipid here. If it binds to the lipid, it's called the glycolipid. So I think we mentioned about something like that before. So that's the glycoprotein, glycolipid. And they extend outside of cell membrane. Sometimes it's also form this sticky protection, sugar coating. So for example, have you ever heard about the A1C? A1C. This one is a term for the diabetes. That is how much glucose coated the red blood cells. And so this one is also called the glycocalyx. So their function is their normal function is to lubricate and protect this cell wall, anchor, locomotion, and for the binding, so they can decorate it, so they can become so they can change the specificity of the receptor to make it become recognized by some other ligand, and they can be recognized, can be used for the immune system. This become the antigen. For example, earlier we mentioned about the virus. COVID-19 can recognize the receptor ACE2, in our cells. So that receptor is a protein, and it can be decorated by the glucose, glycoprotein. And another one is the cell type. For example, cell type is that in the cell type in the red blood cell, RBC red blood cell would have this glycoprotein attached to it, and this glycoprotein will define the type of your red blood cells. Type A will have different, this will be the antigen, this will be the antigen. Antigen. Type A will have type A antigen. Type B person will have the red blood cell. And here we have is a glycoprotein or glycolipid attached to it. And then it will have type B antigen. So this one will have, for the type B blood, it will have a type B antigen attached to the red blood cells. So here are what we just talked about. For example, here is the lipid, and here is the carbohydrates binds to the lipid. Then this one is called glycolipid. Here, glycolipid. If this is protein, this is the protein, this is the protein, glucose binds to it, carbohydrate binds to it, then this one is called glycoprotein, right here, glycoprotein. And if it's very large out there, we don't have the proteoglycan here, proteoglycan. We don't see any proteoglycan here. Okay. And then this one we have the so here is the proteoglycan. Proteoglycan usually is very large, very extended structure. They are the major one to fill the space between cells. So our cell is not like our space, like one star, one planet, and isolated from other planet, and it's empty between. So it's not like that in our cell. In our body, all cells in this environment, in this extracellular space, is all filled by large of these proteoglycan. So that's the membrane. So we have the membrane structure, lipid, protein, and carbohydrate. We know that lipid protein can have several functions. One is to provide a channel for passive diffusion. Another one is to provide the active transport. So when we talk about the active transport, let's say we know that cell has this pump. It can pump 3 sodium out and pump 2 potassium in. Okay, so this is called the sodium potassium ATPase. Okay, and if we have this in our cell, what is the consequence? What is the consequence of the cell? There are 2 consequences. One is that because we pump potassium in, pump sodium out, one consequence is that we will have a lot of potassium here and a lot of sodium out there. So this will create the compartment of sodium and the potassium. More potassium inside, more sodium outside. So that's one consequence. First one is so potassium inside, sodium outside. So that's one consequence. What's the second consequence? These two numbers are not even, right? So we have 2 potassium in, 3 sodium out. Sodium is plus, like positive charge ion. Potassium is also a positive charge ion. So when we have less positive charge ion going in, more positive charge ion going out, it will leave this inside to be more positive or more negative. It will be more negative because there's less positive going in, there's more positive going out. So this will leave the environment to become negative. So the second consequence is that inside of a cell, it will be more negative. Outside of a cell will be more positive. Okay, so that's very typical for all cells. All cells have this consequence. Intracellularly, more potassium. Extracellularly, more sodium. Intracellularly, more negative. Extracellularly, more positive. And that leads to the beginning, the foundation of the electrophysiology, that cell has the cell membrane potential here, membrane potential. Membrane potential is a measure inside compared to outside. So here is a measure inside cytosol, inside compared to outside. And it's always negative. So when we measure this voltage here, it's usually around negative 70, 75, 70 millivolt. Okay, so that is very typical. Inside of cell is negative compared to outside, and it's usually around like 70 millivolt. It depends on the cells, but it's always negative. All cells, we will see that negative voltage in the cell compared to outside, and that's all coming from this sodium-potassium pump. So this leads to the intracellular, extracellular ion disparity. That one thing you need to know, although there are a lot, one thing you really need to know is that everything is more outside except the potassium. And the inside of cell, only potassium is more. So for example, potassium is more inside compared to outside. Sodium, calcium, chlorides are more outside compared to inside. So that's something. So what's more in the cell? If I have the quiz question, potassium, sodium, calcium, chloride, etc., etc. What's more compared to intracellular to extracellular? Potassium is more inside of cell. So this membrane potential is driven by the major player is the sodium potassium ATPase. There's a second one. That's because, say we have this pump, right? We have this pump. We pump K plus in, sodium out, 3 out, 2 in. And if we keep pumping the 2 potassium in, would that overflow? Would that become too much? It will be, right? If this one is like a restrained, like fixed environment, it will become burst, like just way too much. So there is a little like leakage here, leakage channel here. Sorry, I don't want that. All right, so there will be a leakage here. Mark pencil. There will be a leakage here to that potassium a little bit. It's not a lot. So when it's like you have the bottle of the water and you keep filling water, but you have a little hole here. So little water will go out and you can keep it almost the same level all the time. So to maintain the membrane potential, we have two major players. One is the ion pump. The other one is the leakage of potassium. And this channel is called leakage channel. So that's that. Here we have the sodium, potassium all have some leakage, but potassium has more leakage than sodium. And here we have the sodium potassium pump to pump sodium out to pump the potassium in. And the leakage is to make the potassium leak out. So we pump it in, but you let it leak out a little bit. So it can maintain that the potassium is not overflow, right? So that is the membrane. And then let's move on to the next one. The next major one is the nucleus. Here is the nucleus. So organelle, we have this organelle. Organelles has two groups. One is called non-membranous organelle. The other one is membranous organelle. Non-membranous, no membrane. Membranous organelle has the membrane. So the one we just mentioned is the vesicle, is a membranous organelle. Now membrane has two major ones, cytoskeleton and the ribosome. Membranous organelle has a lot, nucleus, ER, Golgi apparatus, lysosome, mitochondria. So let's start by talking about this non-membranous one. Cytoskeleton. Cytoskeleton is, if you can look into these cells, you can see a lot of structure here. These are the skeleton of the cell. It's called the cytoskeleton. Cytoskeleton has three types. From the thinnest to the thickest are microfilament. You can see that this microfilament has little bits like connect together. Each of these bits is called actin. So each one is called actin. Each of these bits is an actin. And so it's composed of the actin protein. Intermediate filament is more durable. This made by like collagen. So this is very durable. This and the largest one is called microtubule. Microtubule basically is a tube. So inside is hollow. You can see that it's also made by this little protein, little bits. Each of these bits is called tubulin. Right here, tubule. So each of these bits is called tubulin. T-U-B-U-L-I. Tubulin. So microfilaments, microtubule are composed of the monomer. So this basically is a polymer. And so they can decompose very dynamically. Intermediate filaments are more durable. They are more stable because they are made by the collagen. These collagen fibers are not that easily to be decomposed and recomposed, disassembled, reassembled that easily. So they are more durable. And but one thing you need to know that from the thinnest to the thickest is the microfilament, intermediate filaments, and then microtubule. You need to know that, okay? That is a quiz question, that from the thinnest to the thickest. So here, from the thinnest to the thickest, microfilaments composed of protein actin. Intermediate filaments is more durable, composed of several different things, but one option, one component is the collagen. Microtubule is made by the it's large, the largest hollow tube, and the protein is called tubulin. Microtubule has a lot of story to talk about. One is that it can be the real system to move vesicles. It can form the spindle apparatus during cell division. It can also provide a structure for cilia and flagella. So let's look at this. So this is a cilia. You can see that this is a cilia. And in this cilia, sometimes we have about nine like a group of the microtubule. Each one can be 2 or could be 3 microtubule grouped together to form this cilia. You must know that this cilia can move, okay? So they can weep, and they make the cell to move. This is made by the microtubule. So that's another quiz question. What's the main structure to construct, to provide the structure of the cilia? That's microtubule. So the quiz question could be one of these, right? Microfilaments, intermediate filaments, microtubule. So you must choose the microtubule. And this is the flagella. It also have this structure, this microtubule to support it. They can move, they can weep, and they can make the cells to move. Also, the cell division, when we have the chromosome to be duplicated, and at the time that they need to be divided, and that pooling is provided by the microtubule. So here you can see microtubule, right here, microtubule. So this one, every one of this is microtubule to pull these two apart, and then 2 cells can be separated to form 2 cells. Also, they can move vesicles, okay? Remember that we talk about vesicles when we talk about the endocytosis. For example, they can be endocytosis and then move, right? And how would they move? They can move by simple diffusion. Simple diffusion is like passive diffusion. They don't know where they go, right? Or they can be loaded on a transportation, like on a bus or on a train to move. And that, if this bus, it will be on the highway to move, that highway will be the microtubule. So it's microtubule. So this one is an example of the nerve. So it's called the exon transport. Or it can be, if it's highway, then this is rail to load on it and then move. So that's also provided by the microtubule. Another non-membranous organelle is the ribosome. Okay, we talk about ribosome. Ribosome is the organelle, but it's a non-membranous organelle to conduct the protein synthesis. So ribosome basically has 2 subunits. Then they like a hamburger, and they will bind together. Inside of it is the RNA. RNA goes in, proteins going out. So it's a magic box to produce protein. So its function is protein synthesis. Ribosome has 2 forms. One is free ribosome. The other one is fixed ribosome. A quick question could be that, where can you find a free ribosome? It's in the cytoplasm. It could be, the question could be that, ER, nucleus, extracellular space, or cytoplasm. So free ribosome is in the cytoplasm. Basically, it's in the cell and it's freely located in the cell. And the fixed ribosome or membrane-bound ribosome is attached to the endoplasmic reticulum. And then they can generate protein for cell membrane, for lysosome, or to be secreted. We will talk about their function later. But the thing you need to know is that there are two groups of ribosome. One is free, the other one is membrane bounded or fixed ribosome. And you need to know their location. For the fixed one, it's fixed to where? ER, endoplasmic reticulum, okay? So this one is a figure showing you that the burger I was talking about, the ribosome has two subunits. If it's inactive, these two are, floating around. But when they see the job, then they will bind together and they catch this RNA. RNA goes in, proteins going out. Okay, so these two subunits, when they are inactive and they bind together, RNA goes in, protein goes out. So here is the translation of the ribosomes right here. So first we have the DNA to RNA, messenger RNA. Messenger RNA will go through this ribosome. Two subunits bind together, messenger RNA go through it, and here it produces this polypeptide. This is primary structure of the protein. Before any foldage is there, but it's not completely functional yet. You need to be folded to make a certain structure to a certain product. So the location of free and the membrane-bound ribosomes are either in the cytoplasm or in the endoplasmic reticulum. So the job of the ribosome is to produce protein. So for the free ribosome, it's like this one here, it will generate the protein. And when it's generated, it will just release that protein in the intracellular space, leave it there. But if it's a membrane-bounded or fixed ribosome, it's fixed where? ER, right? Endoplasmic reticulum. So when it's produce the protein, then they will insert this protein into the ER. ER is a membrane-bound structure. And from there, they will conduct a lot more process. Then it will transport, stored, packed in the vesicles. And then from there, it can be either moved to different organelle, such as lysosome, or move it to the extracellular space. Let's look at this one here. For example, that's this one here. This is the ribosome. It's a fixed one. They will produce the protein. This is ER, endoplasmic reticulum. And then it will be, first is the primary structure, is a linear structure. Then it's folded and it's packed in the vesicles. Then this vesicle will be pinched out from these vesicles. The next step is going to the Golgi apparatus to do further process. I think we have a picture. In my last lecture, we did talk about that, right? Maybe we have a picture here. Let me see here. All right. So for example, that from the ER, these vesicles got pinched off, then moved to the next step. That's the Golgi apparatus. It will be further modified, further folded, then it will move inside, packed in the vesicles, then get released into the extracellular space. Or it can be, let's see if we have here, yeah. So for example, this is ER Golgi, then pinch it off, release into the extracellular space, as we mentioned earlier, or it can be these vesicles merge with the lysosome. So it will be deliver that protein. In this case, these proteins are digestive enzyme in the lysosome to help the lysosome to digest this engulfed stuff, right? This is bacteria, for example. So that's how basically the major job that your cells are doing like every day. Your DNA things will be transcribed into the RNA. RNA will be translated to the protein through the ribosome. If this ribosome is free, then it will release that protein in the intracellular space. If it's fixed ribosome, then the protein will be packed in the vesicles. And when it's packed in the vesicle, there's only two, not only, but two major destinations of that vesicles is that it will be either released in the extracellular space or it will be moved to the other organelle. And in the case of merge with the lysosome, this protein could be the, the digestive enzyme to help the lysosome to digest the food. So those are the non-membranous organelle. How about let's take a rest? Yes, and we will come back from this membranous organelle.